Okay, thank you everyone for coming along. This is the 10th simulation summer school session this year. I'm joined here, or we're joined here by Oscar Olvera Astivia from the University of Washington. He's a assistant professor at University of Washington, specializing in statistics, simulation, things like that. And we're really excited to have him on board for this for simulating multivariate non-normal data using the NORMA package. NORTA package, sorry, I'm getting confused. NORTA. Okay, so I'll pass over to Oscar now. As before, I'll be on the chat, and there are materials for you to check out on the OSF page. So please go there if you've to get the materials. And yeah, over to Oscar. Thank you.
Hey, hi, thanks, Oli, and hey everyone. As Oli said, hi, I'm Oscar, University of Washington assistant prof in measurement and statistics, and I specialize. This is the kind of workshop I really like to give because it goes right into my area of research, which is the simulation of multivariate non-normal data. I'm just going to deal with a continuous case this time around because the discrete case is a whole other beast, which is super interesting as well. I know that it's a bit weird or peculiar because I know that as you go through like the kind of programs that specialize in methodology, in statistics, in the social sciences, you usually pick like an area, right? Like I'm going to specialize in identity response theory. I'm going to do cerebral equation modeling, and from then you say like, well, I really like fit indices. I really like all of these things. Because of the constant use of simulations that I have, like I know that my program of research is a bit peculiar because I said like, no, I don't want to do any of those things. I want to understand the tools that we use to understand these things, because I feel like informing this piece of the puzzle informs all the other pieces of the puzzle. And boy, what a ride it is and it has been. And I'm hoping that throughout this workshop, I'll be able to convey some of the insight that I have developed as I sort of like study these things. And also, I'm going to be sending you tips to everyone of things that I have been noticing as a reviewer of simulation papers, because now I guess now people realize like, oh, you do simulation stuff. Here's all of our manuscripts that do simulation. Check them out. And I've been noticing a lot of patterns in terms of kind of little ambiguities that people do. So I want to make sure that I use this time not just to train you or help you to understand how these methods work, but also when you become a consumer of simulation research and understand and read simulation articles, you can start like spotting or like, there's a bit of problem here. There's a bit of problem there. Like I am just writing a manuscript right now that specializes in a different method. And literally every article I have checked is like, that's a problem. That shouldn't be there. That is ambiguous. That is not. So I'm like, there's a lot of work that needs to be done here. So I wanted to like preface this starting thanking Oli and Jenny for having this space for all of us to sort of like learn and understand these things, because there's simulation is a very powerful tool, but it's also very easy to misuse it. I prefer to encourage people to ask me questions as I go around. I love interruptions. It's like my favorite thing to do. And I also feel like if we address them at the moment that they present themselves, it's easier to sort of like clarify that misunderstanding and then build across. I know some people would say like questions towards the end. I'm more of like, questions when you feel like them. And now, just as a minor thing, Oli, would they be like sending questions like through the chat? Would they be like asking questions like unmuting themselves? I'm okay either way. I just want to make sure I'm prepared.
However people want to do it. So you can either put your hand up, and if a question comes up, I'll keep an eye on the chat. And if a question comes up and you'd rather chat, I can butt in and ask it by chat. That's probably how it will work. Okay. So yeah, hands up or just in the chat, and I'll address them as they come up.
Awesome. Let's do that. Because sometimes like kind of like monitoring like my screen and the chat box kind of be like and because I'm one of those people who writes a lot, I'm going to be writing like jumping between like slides and notes and a bit of R code. So I'm hoping that everybody can follow along, because I don't know, I think it's a lot easier to learn things if I demo them and you do them on your own as well. Okay, perfect. So thanks everybody for sharing these hours with us, and we're going to get started a little bit more formally. Now, this is a little bit of the agenda that I have in mind for today. I am sort of like the first 2 points, the probability integral transformation and the matrix factorization approach for normal data, apologies, I didn't really, it's a bit interesting to start these type of workshops, because it depends on the sort of like level of understanding people where to start. And I'm starting from the understanding that people do not know these things. And they don't seem very related to the process of simulation, but you're going to see right away why they become crucial to understand the simulation process, because pretty much every method that you will learn or read about in our published articles, in our published journals, deals or is conceptually related to these type of approaches. Then I'm going to be using that as sort of like the problems with using this type of methods with non-normal data to introduce the NORTA method, which is an acronym for normal to anything, and how we use these to sort of like work around the issues that work with normal data but do not work with non-normal data. And then finalizing with what I think, well, actually, I don't think, I know because I have spending quite a few years doing this type of research, is the most popular method to simulate non-normal data in the social behavioral sciences, which is the third order polynomial method. So that's sort of like an overview of what we're going to be looking at today. So without further ado, let's start. So the probability integral transform. It is the most basic and the most general approach to simulate mostly univariate, doesn't have to be univariate, but mostly univariate data. And it goes by many names. I've seen it as the inverse method, the inverse sampling method. For those of you who took the workshop with Lisa, I always mispronounce her name, Dr. Lisa de Bruyn. She uses this method to transform across simulations, across distributions. Like it has these functions in her full package that says like normal to these or exponential to that distribution. And when you pick inside, what the full package is doing is the probability integral transformation. And it really just needs to have two things. You need to have a way to evaluate a distribution's cumulative density function, which we'll be explaining for in a few seconds. And you need to have a way to simulate random data. This U stands for uniform, in case this is new, in the interval of 0, 1. The uniform distribution, for those of you who are unfamiliar, is essentially what I think most of us understand or think about when somebody says like doing things randomly. It means it's a distribution where every outcome is equally likely. And it's a continuous distribution. And in this case, any number in the interval between 0 and 1 would be equally likely. Now, the way this works, and it's super straightforward. I'm going to stop sharing and jump into R. That's part of the script. Is basically you start, actually, it might be better to start with the notes for those of you who are unfamiliar with how the uniform distribution works, which is, so the uniform distribution has this shape. That's like a rectangle that goes from 0 to 1. As it happens, the uniform distribution, because probabilities also range between 0 and 1, this thing can be transformed into any number of distributions, right? Like the normal, or the chi-square, or the exponential, or the Laplacian, or anything. Essentially, as long as we can use this thing called the inverse of the cumulative density function known as the quantile function, so the CDF versus its inverse called the quantile function. We should be able to turn anything, to turn this funky little rectangle with that exists in between 0 and 1 into literally any distribution whose cumulative density function we can evaluate. Now, to get a little bit of a sense, an intuition of what this thing is, if you use so P norm, for example, that's the CDF of normal distribution. This gives you give it a z-score or a value of normal distribution, and it gives you back a probability. So if you do P norm for a normal distribution that has a mean of 0 and a standard deviation of 1, you're going to get 0.5. Right, because the standard normal has a mean at 0 and it divides the probability into equal sections. Now, the inverse of the CDF, or also known as the quantile function, Q norm, this basically takes a probability, like we could do 0.5, and gives you, in this case, the z-score, because it's using norm, that would correspond to that probability. So, for instance, if you were doing something like Q norm, let's say 0.02, actually 0.975, 975, mean of 0, SD of 1. Like we've all seen this magic number, right? 1.96, which of course gives you the top, and like it divides the 0.25% and 2.5% on one tail, 2.5% the other, like our magic 5%. So every time that you're using R or anything and you get a p-value, somewhere in this process, there is this inverse CDF function that is sort of like checking out the areas and giving you the value, or the other way around, the p-norm function that checks out the values and gives you, that's probably the one that you're using to check out the values and gives you the area under the curve. So how does this pertain to simulation? Well, R or most packages, like it's a whole area of research to be able to randomly simulate numbers between 0 and 1. Because if you can do that, you can pretty much simulate anything using just like statistical properties. So if we declare a variable of something that goes between 0 and 1, and we ask R to give us this inverse, the inverse CTF, the quantile function, and say like, oh, let's see what the histogram of breaks of Y looks like. Breaks. I didn't do this right. Then you'll see that it becomes a normal distribution. So this is going to be sort of like this Q norm function, the inverse of the CDF, is sort of going to become kind of like our universal translator between probabilities and different shapes or different distributions, which is going to become very, very useful once we start dealing with something that goes beyond the zeros and the ones. Yeah, so I have like my little thing is like, oh, look, it goes from a rectangle, and then it becomes like a little normal thing. Now, what's the intuition behind it? Like, because this is a lot of this stuff to sort of like get really well, you need calculus, and I'm not really assuming a calculus understanding of this, but think about it this way. If you can get a cumulative density function, you can evaluate it somehow. It's always going to have this sort of like funky little S looking things. Well, it's not always going to be, but it's always going to have, it's always going to exist between 0 and 1. Just goes right here. This is in the interval between 0 and 1. And here, what you're going to have is whatever domain of the distribution you have, right? If it's chi-square, it would only be the positive real numbers. If it's normal, well, it's everything between negative infinity and positive infinity. And what you can see is that this function essentially maps the range of 0 and 1 to values all across the number line, in this case of the normal distribution. You can see the steepest slope is around the 50%, the 0.5% area, which is, of course, where most of the mass or most of the probability of the normal distribution is concentrated. And as you go towards the extreme, you know, 1 standard deviation, 2 standard deviations, 3 standard deviations, 4 standard deviations. Well, the probabilities start becoming smaller and smaller, right? So that if you want to have a change in probabilities, you actually need to really move very far away into either the positive or the negative direction, right? For these different areas. For instance, when you are at 2 standard deviations from the mean, assuming once again a standard normal, well, you're already pretty much to the number 1 or 100% of the probability. And of course, by the time that you get to 4 standard deviations from the mean, you basically have already used up all of the area under the curve because it's getting really, really close to 1. Of course, these are asymptotes right here. This thing never actually reaches 1, or it never actually reaches 0, because it happens all the way up to infinity. So the intuition that I want to sort of to keep from this section, or to this understanding, is, okay, so I have this thing called the probability integral transformation. It's really a very fancy name for a technique that's just apply the inverse of the cumulative density function. This is the cumulative density function, this kind of like weird sigmoid looking thing. And this allows me to grab numbers or random variables that exist between 0 and 1 and turn them into many types of other distributions. Of course, assuming that I have a way to reach or evaluate at different points the cumulative density function. So new things, okay, cumulative density function, that I can either use that to get numbers between 0 and 1, an inverse cumulative density function that gives me numbers from 0 and 1 into all of the range of the distribution of my choice. Okay, so that's the first part. Now, what if I don't know the CDF? Well, of course, this is not a method that we use very often because not all distributions have cumulative density functions. Well, they have to exist, but like they're not always like in this very nice form that we can evaluate. So usually we need to approximate them somehow, and and it can get really out there into the into the weeds, which is why most of the time we just want to be seeing this method used for univariate distributions whose properties we know very well. I did want to use, for instance, the case of the normal distribution because it's probably the best known distribution that we all work with. And the cumulative density function of the normal distribution, as you can see, cannot be, it's not like a thing that you can just plug in numbers and get them out. Because these have this funky integral that is known as a Gaussian integral, as well, a family of integrals. And these things can be notoriously difficult to sort of like evaluate and get like a closed form, like a formula type expression. But because this type of, well, not just integrals, but the normal distribution is so popular and so useful in most of the things that we do, we have developed a whole bunch of algorithms to evaluate this integral with like very good precision. And and these can be sort of like hyped up, moved up to the multivariate spaces. But of course, for every dimension, you need to add another integral, and then this whole thing kind of like becomes a little bit bonkers. So it's been quite an interesting ride in terms of like how we got from remember those tables of p-values that used to be on the back of textbooks to now having everything here like in software and sort of like really flexing this computational power that I guess the 21st century has afforded to us. But it's just the point of for you to keep in mind of like, okay, so there's this thing called the CDF, and for this thing to work, or for the next few methods I'm going to be investigating work. For the next few methods I'm going to be investigating to work, we need to be able to evaluate this inverse CDF or the CDF in one way or another. So that is sort of like all that we need to understand for this part of the agenda. It's like we have our universal translator, the uniform distribution, and we have this method that changes numbers between 0 and 1 into other distributions that we want. So from the univariate to the multivariate normal, so linear combinations of normal variables. Let's start with a standard normal. So Z is distributed as normal with a mean of 0 and a standard deviation of 1. One thing that we can do without having to invoke any functions in R or any software of our choice, if you say, well, but I don't really just want to work with standard normal variables. I want to work with general normal variables that have like a mean or a variance standard deviation of my choice. Well, one of the easy things that we can do is say, well, is just apply this simple linear transformation, right? For A and B being constants, if we just define a new random variable that I'm calling X here as A plus B and Z, now X is still going to be normally distributed. So the multiplying and adding didn't change the properties of the distribution itself. What changed were the population parameters. Now this X has a mean of A, my intercept right here, and a variance of my constant here, B squared. And for most cases, as long as the distribution is standardized and that it has finite moments. So like I'm thinking about the Cauchy distribution. For those of you who haven't heard of that one, Cauchy distribution is the T distribution with 1 degree of freedom, is the sampling distribution of a ratio of standard normal variables, and it's notorious because it's usually a counterexample to everything. It has no moments, it doesn't have a mean. Well, so it doesn't have it's undefined, and the variance is infinite. So yeah. For those kind of things, this trick won't work. But I'm pretty sure that for most of the things that we are working with, this trick would work to sort of like induce a mean and a variance, like they usually are known as location. Like this technique creates what are known as location scale families of distributions. Location because the intercept gives you something that looks like a mean, and the scale because this constant B gives you something that looks like a variance or a standard deviation. But sort of like the key aspect to remember, at least from this part, is that doing these linear transformations keep the properties of normality, only changing the moments, the parameters of the mean and standard deviation from 0, 1 to A and B. And if we look at that in R in our example, so what we can have right here, you start with R norm, of course. This is R for random variates from normal distribution. I'm using 1,000 here, means 0, standard deviation of 1. So something close to 0 as a mean, something close to 1 as a standard deviation. Let's say that I want to use, well, I guess this mean would be, I wrote 5 there. And let's just make 5, 10 here. We do this simple linear transformation to create X. And now we can see that, oh, the mean has moved from 0 something to 10 point something. And the variance of this new random variable has moved from 1 to something close to 800. And if we were to graph these, we would see a little bit of the differences, right? Of course, this green distribution right here, well, that would be what we started with, the normal distribution, because it only has a variance of 1. So it's very narrow. It's shrunk around the mean of 0. And then this sort of like pinkish, reddish type distribution, well, that is the one that is our new transformed random normal variable that has a mean of 10. And of course, it's a lot more, it's not as narrow because the variance has now moved from 1 to 10. So, okay, simple linear transformation, but of course, the important part here for us to keep in mind is that the property of normality itself, this is not a non-normal distribution. It keeps its normality properties, for a lack of a better word. And you can do that, check that if you do Kolmogov's-Smirnov test for my new random variable X, and you have to give it the CDF with, what is it, mean of 0, I think, mean of 10, standard deviation will have to be the square root of 10. Let's see if this works. No. P norm, mean 0, standard deviation test. No, I'm going to be missing that. Ah, there you go. Oh, it's not giving me the, let me add a few more zeros here. Let's see if this works. Ah, it's still not giving it to me. Well, usually when this thing works, this is the kind of thing you get with live coding. Like this would be a p-value greater than 0.05. We're going to be relying on this Kolmogov-Smirnov technique, sort of like to remind ourselves that a lot of the things that we're doing are not altering the properties of the distributions that we are working with. But I guess that's what you get sometimes for doing these things without testing them. So this is a bit of the graph that we're working with. But this gets exactly to what I wanted to get, which is this idea of closure under convolutions, or which is also known as closure under linear combinations. So let's start by saying I have 2 standard normal variables, which we know how to work with and how to simulate. So we're going to call them X and we're going to call them Y. And because I want to have like the more sort of like general version, definition of the, oh, there's 2 questions in the chat. Would it be squared?
More comments than questions, but yes.
It's because you're running into the next not said. Oh, good point. Thank you. Appreciate that. So we have the standard, these 2 new normal distributions, and we're defining a 3rd random variable, which is called W. And W is going to be the sum of X and Y, as before. And when we do that, we end up with another normal distribution, which is the distribution now of W, where the parameters are going to be the sum of the intercepts and the variances are going to be the sum of the variances. Of course, assuming, and this is very important, they have to be independent for this thing to work. So that W, once again, does not lose its property of normality, but it alters or changes the parameters, very similar to what we're doing above. Now, the reason why W is still normally distributed is because the normal distribution, among all the interesting properties that it has, is closed under convolutions / closed under linear combinations, which means if you add any number of normal distributions, what you're going to end up with is another normal distribution. Now, this property is shared with quite a few other distributions as well. The chi-square distribution is closed under convolutions. The gamma distribution is closed under convolutions. The binomial distribution is closed under convolutions. But most distributions that we work with are not closed under convolutions or closed under linear combinations, which means when you start adding distributions, even if they come from the same family, you may end up with something that is not what you intended, or that is perhaps a distribution that has well-known forms. For instance, the sum of exponentials is a gamma distribution, but does no longer have the properties of non-normality, perhaps the moment, skewness and kurtosis, or outlier, something that you may have intended in the beginning. And this is going to become very, very important when we start moving into sort of like the NORTA method approach, because kind of like little newsflash, perhaps the most egregious issue that I find when I'm reviewing articles is when people start playing with the distribution, the distributions that they're going to use for simulation, and they haven't checked whether or not the distributions that they're using are closed under convolutions or not. Because then when you do that, you're like, oh, now you're working with a distribution that no longer resembles what you thought you had in the beginning. But you're continuing through the article as if these were the case. Happens a lot more often than you may think. So first thing to keep an eye out from, if people are doing simulations and like they're adding them, or they're adding random variables, they're subtracting them, they're doing operations with them, always check, wait, like, is this thing closed under the operation that people are saying? If I'm adding two distributions like this or random variables like these, am I getting these different type of random variable or not? It's going to come out very soon. Very important. And yeah, I have sort of like my little graph here just to once again show you that now the mean has changed to whatever we're using here. I think in the example that I had, what am I using in the example that I have in the R code? Tens and 20s. Yeah, I am not the most creative person when I come to using these things. And it's working as the way you expect it. It's like, okay, so now the mean of W is something close to 30. The variance of W is close to something that'd be like 500. And so yeah, of course, so that makes more sense here with the mean close to 30 and the variance being something like 500. So okay, it's cool to play around with distributions and doing operations in them. We just need to be mindful of what we are going to end up with at the end. Okay, so this is where things start getting interesting. Now, let's say that we start with two standard normal variables again, and they have we assume them to be IID independent and identically distributed, which is normal with means 0, 1. And now we're going to define these random variables. First of all, we're going to make sure that x equals just its standardized version. So this one keeps its 0, 1 mean. And then we're going to have y. But for y, we're going to apply this particular linear transformation, where we're going to have a parameter rho, surprise, a correlation coefficient that ranges only between 0 and 1. And then we're going to have sort of like what I guess you could call, like in a weird way, the unreliability or the lack of correlation between two variables. So we have sort of like the part that is going to be shared between these new variables x and y, and the part that is going to be unique only to y. Now, when we apply these type of transformations, the first thing that I always ask people to do is check to make sure that the moments that you're working with are still the same moments that you would intend. So x keeps the same parameters, like a mean of 0 and a variance of 1, same as zx, because of course we're making these we're making x equals zx. But what happens with y? Okay, so y is defined to be, let me start erasing a bit of this just to clear off some and start highlighting terms. Okay, so y is now this thing, which is what we have right here. Now, because the expectation operator, because of the linearity of the expectation operator means we can sort of like divide these in chunks. And very importantly, we're going to be referring to this in particularly the independent part to get the results that we need. Well, that means that there really are only two random variables here, zx and zy, for which we would need to calculate an expected value, right? Because we have already assumed that rho is a constant that exists between 0 and 1, which means this number is also going to be a constant. So the expected value of a constant is constant itself, or in this case, we can just take them out once we have sort of like divided the expectation, and they sort of like leave outside of the operator. Now, because these things are standard normally distributed, of course, their expected value is going to be 0. So all of these things is going to cancel out. It's going to be 0 plus 0, which means the mean of y is also going to be 0. So check. We know, we kind of know what we're doing here. That's the second thing to kind of have a look at when you're looking or into articles that do simulations, which is like if they start applying these little things, you know, if you say that we're going to increase the variance when I reduce the variance by a factor or something, always like, wait, those adding or removing these constants, those multiplying these constants changes the properties of the distributions. This is a little less common, but I have, you know, found it a few times, and, you know, every now and then you sort of like have to run them through the thing of like, well, you know, to do the expectation, you separate, and if you don't end up with something that the authors claim it is, with what it is, problems. So at least we know that using this transformation, we still keep the a mean of 0, which is sort of like what we were expecting when we're working with these things right here because of the properties or the moments of the standard normal distribution. Now, what about the variance? Okay, so the variance has this property now. It also, because of the independence part, right? Because when we have the variance of a sum, let's say, of x plus y, and we don't know anything about x of y, is always going to be the variance of x plus the variance of y plus 2 times the covariance of x and y. Of course, if we are throwing in this assumption of independence, then this thing goes away because the covariance would be 0 since they're independent. And we're only left with the easy case of the covariance, the sum of the variances, of the variance of a sum being the sum of the variances. We'll just want to work on that. Or sorry, work with that. Which means we can once again sort of like pull out the constants, but in this case, because we're working with the variances, we pull out the squared of the constant, not the constant itself, which is what we were doing when we were working just with the expected value. So moving these ones out means where once again I end up with my constants outside of the variance operator. The variance of these things, well, because they're standardized, is going to be 1, which is this one here and this one here. Well, of course, these constants multiplied times 1 do not change, but I have a positive and a negative row, so these things cancel out, and now the variance of y is going to be 1. So mean of y equals 0, check, working correctly. Sigma square of y equals 1, check, just what we expect. Now, last but not least, because now we have, of course, 2 random variables, and we have induced this sort of like relationship between themselves, now we have the covariance. And the covariance, it works a little bit, of course, we're working with the assumption of independence, at least from the get-go, and it still works kind of like what we would be looking at with the expected value, in the sense that these constants are coming outside of the operator when we're evaluating or like calculating these things. Now, in this case, the covariance of zx and zy, well, we assume them once again to be independent, so we end up with a 0 right here. In this, and the other thing to realize for us is, of course, the covariance of a random variable with itself is its variance. So the covariance of zx with the zx becomes the variance of zx, which we already know from here is equal to 1. And because we pulled out the correlation parameter rho, we end up with the covariance for this particular transformation being equal to the correlation coefficient. This is sort of like a pretty old method to generate bivariate normal data. There's a few ones, but it's the oldest one that I could find, and the one that I find the most often taught and used sort of like when we're working with simulation-y things. So that we end up finally in full generality now, what we would be a bivariate normal distribution that has its parameter, its vector of means being 0 and its variance covariance matrix well being, of course, because these things are standardized, they have the covariance, the correlation as their the value of their covariance. Now, because the Pearson correlation rho is also invariant under linear transformations, we can use the techniques or the tricks that we have learned in the past about the normal distribution being closed under linear combinations, closed under convolutions, to sort of like define in full generality what a bivariate normal distribution would be like. Just applying these linear transformations to x and y. Now we're changing the vector of means for it to be a and z, and a and c, and I have the variance covariance matrix. Now, of course, the multiplication is going to turn these numbers into the square of the slopes, and the covariance, like in cases new to people, the covariance of a random variable is equivalent to the product of its correlation coefficient and its standard deviations. I think I have a funky thing in R for us to verify as well, that what we're doing here is actually what we would get, because it's something that I do a lot, like especially like when I'm working with like pen and paper and pencil math. It's like, wait, did I trip myself? Am I doing something wrong? It's like, let's ask Art and see what we check. So I'm starting with a correlation of 5. I'm increasing the sample size a little bit more here to make sure that we sort of like remove a bit of the sample to sample, I guess, well, not bias, but you would expect these things to change because of course the random variables are changing. The mean and variance of x, well, they stay the same as we say. The mean and variance of y, well, as we saw when we were working through things, stay to something close to 0, something close to 1. And the covariance of x and y, well, it's now something close to the correlation coefficient rho as well. And if we were to apply the linear transformations just to sort of like work with a fully general bivariate normal distribution, well, then we'll see, okay, this thing matches 10, this thing matches 20, which is what we would expect here from the intercepts, 10 and 20. This thing matches the variances for 100 and 100. And of course, for the covariance, well, this would be something close to 100 as well, which is 10 times 20 times 0.05. So R gives us the go. We know that we did our hand calculations correctly. And at least we are now learning, okay, so we now know that through these properties of being closed under linear combinations, we can actually induce a dependency, a linear dependency, which is what we were looking at right here. Now, I guess this is not super new because when we say, well, yeah, we have known this since like simple linear regression. You know, you have one predictor, one dependent variable. If you keep on adding the error, then of course you keep on either reducing or increasing the association between dependent and independent variable. I guess just sort of like conveying that if you select those terms, like, you know, a bit more like mindfully, you know, with these specific ones, you're going to end up exactly with the correlation coefficient that you want. I mean, it's not something that you cannot like sort of like trick your way into it if you keep on trying and error, but I guess it would be convenient to say, oh, this is sort of like the one thing that you need to sort of give it so that you end up with a correlation that you want. So that's only for the two, the bivariate case, right? What happens when we have the more general case, when we have P random variables or P sort of like columns of normally distributed random variables? Well, in this case, of course, we're going to start working with a variance covariance matrix or a correlation matrix, depending on. I tend to use those interchangeably, but I always work with a correlation matrix. Just sort of like highlight, say like, well, that's a covariance matrix. Like, I know it's a bad habit I developed. I'm sorry. Now, what's important here is that to remember that the variance covariance matrix, well, most square matrices have some type of decomposition. And I wanted to use the spectral decomposition or the eigenvalue decomposition particularly because of its connection with factor analysis. You'll see that I'm even using sort of like the names of the matrices that we see in factor analysis on SEM, right? The matrix of loadings and the factor correlation matrix. So I guess in the part of the reason is to highlight that the spectral decomposition of a correlation matrix is implicitly tied to what we do in exploratory factor analysis, which is what we know as the matrix of loadings is really the matrix of eigenvectors, and we know as the matrix of factor correlations, well, in this case, is a diagonal matrix with eigenvalues. Now, you don't only have to use this type of decomposition. Most people use something known as the Cholesky decomposition. R uses this one though, when you're using you're calling the mass package and use the MVR norm function to simulate multivariate normal data. But this could be a factor analysis, principal components, the Cholesky, like literally any number of matrix decompositions will also do this trick. And then it just really becomes a problem of matrix multiplication. I sort of like emphasized this by adding these little rectangles right here. And I am defining this new random variable that I'm calling x, which is lambda square root of phi lambda transpose. Once you do that, times the transpose of my original sort of like random variable, which in this case is a multivariate standard normal. So it has a vector of zeros as its vector of means and a huge identity matrix, right with ones in the diagonals and zero everywhere else. So like, no, I'm going to work with something that has, that is not independent. So why this works takes, well, it depends on how familiar with this. It takes a bit of while to understand, but this is the best thing I can do sort of like with the time that I have. When you're working, there's an interesting connection, I think, between statistics and geometry. And in this connection, variances work like distances and correlation coefficients work like angles, cosines of angles. Some people may have heard this, some people may have not. So that when you start in this part of the sort of like simulation of generating data, the one that says like, I'm starting by creating multivariate standard normal variables, which is essentially just a series of columns with standard normal random variables. Well, they start orthogonally at right angles for one another. When you use, or when you throw in this matrix decomposition to these standard normal vectors, what you end up doing is basically altering the angles at which these vectors are, so that you're telling them, no, I don't want you to be orthogonal. I want you to be pointing in this direction. I want you to be pointing in that direction. I want you to be pointing this. And because you're asking these random vectors, of course, each one of these z's is going to be one of those random vectors, saying like, okay, so you start here. Then the second one is going to move around with reference to the first one. And it creates an angle that induces a correlation. Then there's going to be another one, which moves, of course, with respect, well, I'm running out of space here because I can only portray these things in two-dimensional space. And the third one is going to say like, well, I needed to have an angle with respect to the first one and to the second one that gives me a correlation. And for each one of them, basically, so you always start with the first one, the Z1. Well, at least this method, what does you have to do anything? The matrix multiplication takes care of that. Starts with like, okay, one's going to be my reference, my Z1. Then Z2 is going to have an angle to Z1. Then Z3 is going to have an angle with respect to Z1 and Z2. Then Z4 is going to have an angle with respect to Z1, Z2, and Z3, and yada, 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 until you have these, I guess, vectors in multiple spaces, all pointing in different directions. But what really is just going on here is just a quick matrix multiplication. If we check this little example in R, so I'm using 4 random variables right here. These are like standard normal random variables. I'm sort of creating this matrix valued random variable called Z. If we do head of Z, oh, I see a.
I was just about to put a comment in the chat. So if anyone's a bit rusty on matrix algebra or linear algebra, I'll just put a video playlist in the chat. That's what it was. It wasn't a question.
Perfect. Thank you. I appreciate that.
Sorry.
You know, it's okay. No, because a lot of these things relies on matrix algebra, and I know that. Well, I was hoping that if anybody had done at least some factor analysis, you know what like eigenvalues are and whatnot. But yeah. So thank you very much, Oli. So this is what I'm calling this Z thing. My sort of like in this case be like a 4-dimensional standard normal. Multivariate normal distribution. And I want to induce a correlation of only 0.5s all across. 0.5 seems to be my go-to number when I'm working on these things. And I'm going to give it a vector of means as well. So what I'm doing here is literally just following the recipe that I was showing on the slide. So like, well, I'm going to do the eigen decomposition of this correlation matrix R. This is going to be, I'm going to call it L. This is going to be my lambdas. They're right here. And I am going to take or create a matrix, a diagonal matrix of the eigenvalues of the correlation matrix right here, which is the E. So if I do a whole bunch of matrix multiplications, right, L like lambda times the square root of the eigenvalues times the transpose of lambda again, and finally times the transpose of the data that I'm wishing to correlate right here, I'm going to end up with something I'm going to call X transpose. I'm going to add my vector of means to X transpose. This is just important to keep in mind when you are sort of like using this method to create data. Make sure that you do all your operations on the transposed data set. Like, I mean, it just saves you more steps. Like, I mean, to do this thing. And then at the end of the day, you transpose the transposed data set so that now X and of X is sort of like my new data set. It has the dimensions that I would expect, 4 columns and 10,000 rows. It would be equivalent to having 10,000 participants and I don't know, 4 items for whatever 4 variables you like. I'm using the describe function from the site package to see, oh, means of 10, essentially 20, 30, and 40, which is what I had here, 10, 20, 30, and 40. And if I do the correlation of X, well, I'm getting a whole bunch of numbers that are really, of course, these things are not going to be exactly 0.5. They're going to be very close to 0.5 because of sample to sample variation. And the larger you make the sample size, the closer they're going to be to 0.5. But of course, we don't, interestingly enough, we don't really want to see like, these things to be precise numbers, because of course that would mean that we somehow got rid to the sample to sample variation, which is not something that we want to do. And as usual, like if I were to say, well, I want to see how like the scatter plot between, let's say, my variable x1 and x4, well, we see that familiar elliptical shape that the normal distribution tends to have. And I'm adding these lines or these axes to say, well, I designed or I created this multivariate normal data. So it has a mean of 10 for my variable x1 and a mean of 40 for my variable x2. So everything is working sort of like the way I intended it to work, at least for the normal case. Sorry. And so that takes care, at least, of the normal case, which is sort of like the background that I needed to assume, or like I needed to remind people before I started jumping into like the more sort of like thorny case of non-normal distribution. Now, this trick of them, what I'm calling the matrix or the covariance matrix factorization approach, it's very effective. It's once again one of those old techniques that's been sticking around because of how easy it is to work, especially in the age when computer power was not as easy to come by. And it works for almost any type of continuous distribution. The discrete distribution case is a bit of a different beast. And I always use the almost any type because in the back of my mind, there's always that Cauchy distribution that would mess up everything. So I want to be a bit careful with the language. The only thing that we need to be sort of like careful or mindful about is that the variances of the random variables have to be the same. So in the first step here, when we're simulating or creating our original sample that we're going to sort of like do this matrix multiplication trick to induce a correlation. Well, all of these are standard normal. All of these have variances of 1. Therefore, I should be able to use the matrix factorization trick and not run into problems. If you don't have the same variances, you're not going to get the right covariance matrix, so to speak. But you can always standardize any most distributions and apply this matrix factorization trick to induce correlations. So of course, the question now becomes, would this work for non-normal distributions, right? Can I just throw in this matrix factorization approach and just get away with creating or constructing multivariate random variables these ways? Let's start with a simple case. You know, we have, let's see if we can create a bivariate uniform distribution. So I have two, like what I call standard uniform distributed random variables, U distributed uniformly. You know, there's that little rectangle thing that I was sort of like commenting on a few minutes ago between 0 and 1. And I am going to be using my trick right here, the one that has the, oh, by the way, if anybody has any interest, if you do this matrix decomposition on a 2x2 matrix, what you're going to end up with is this transformation right here. So the final thing is going to be two things. One's going to be like 1, and one is going to be this rho times something square root of 1. So although I know that this is treated as a special case, and you're going to find it like in blocks, in Stack Overflow and everything, the fact of the matter is that this is sort of like the algebraic version of a more general approach that is because of course, matrix multiplication is just additions and multiplication of constants, right? So you could, in theory, end up with a series of equations that look like these, which of course become progressively longer and more complicated, but it's essentially just inducing these by adding and multiplying things together. So we're using the matrix factorization approach again. For the uniform case, we're equating our first random variable with our first component, the first vector of uniform distributed random variables. And then we're once again inducing correlation of 0.5 using the second uniform distribution. So this is what it would look like. Actually, for this one, I'm going to jump into R because the next steps are going to be interesting. Let me clear up this. So I end up with the correlation that I want. As I mentioned before, every time that you use these things, you know, with random variables that have, you know, equal variances and they happen to be finite and like ideally they will be standardized, so you don't have to like do rescalings later, you are going to end up with the right correlation or correlation matrix. You won't go wrong with this one. Where you're going to be going wrong though, or the issue that we're going to be finding, is that your x2 is no longer uniformly distributed, right? What's on the left here, x1, that's what the uniform distribution looks like, you know, kind of like that rectangular looking thing. What you end up for x2, well, this thing now has a mode, right? It's unimodal. The name of this distribution, this x2, is actually either the tent or the triangular distribution. And it is defined to be as the sum of two uniform distributions, whether they're weighted or unweighted, which is what we're doing here. You know, it's a weighted sum of uniform distributions, so uniform random variables. It doesn't matter. Like, of course, that is going to change what the mean and variance is going to be of the second component, of the triangular component. But the important part here is to remind researchers that this is no longer uniformly distributed. So if you were using the uniform distribution, or like a hypothetical researcher of whom I sort of like found a few more articles and I wished using this kind of technique, this thing, of course, has positive kurtosis, the x2, the triangular one, and x1 has negative kurtosis because of the flatness and the peakness. So through the process of simulation, you're actually altering the conditions that you may have initially hoped for or wished for. So that's going to be a problem. So applying this approach or using this matrix factorization method gives us the right correlation matrix, the right correlation coefficients, but it gives us the wrong distribution. And not only that, what's interesting about this method, one of the ironies of the world as well, I guess, is because as we discussed, matrix multiplication just is a series of weighted sums of random variables. And what happens when you add up a whole bunch of independent, identically distributed random variables? The central limit theorem kicks in. So that if you keep on doing this with distributions that have more and more dimensions, right, that have more and more columns, each subsequent column is going to be more and more normally distributed. For example, an older, like, you know, we're talking about like 40s or 50s times, old random normal generator used to be the sum of 12 uniform distributions. So you can see that, you know, it's not a very good generator. Like, that's why, you know, we used it when we didn't have access to a lot of computer power. But at the end of the day, and I'm sort of like emphasizing this over and over again because I see it so often in published research, not just about published research and manuscripts. I'm like, we need to do better at this, because when you simulate these things, of course, most of what comes out from your conclusions is now suspect or ambiguous, because the process of data generation is changing the simulation design that you originally intended. You're no longer working with the conditions that you originally thought. And it all comes down to this issue of working with distributions that are not closed under convolutions. It's not a problem with a normal, because you know that if you're going to add up adding 2 or 3 or more normals, you're going to end up with a normal at the end of the day. But it becomes a problem with a uniform, because as you know, I was mentioning to you in the past, by the time that you add 12 uniform distributions, so if you're working with, say, a 12-dimensional or like 12 column vectors of uniform tandem variables, and you apply this matrix factorization approach, by the time the sort of like series of multiplications and additions ends up to the end one, if you try and plot it, it's going to look very bell-shaped and very symmetric. So you're basically undoing what you think you're doing with this approach. So here's an idea. What if we start the other way around? Since we now know that the central limit theorem is working against us, what if we start with a multivariate normal distribution, and then we can use the probability interval transform trick to change the shapes of the marginals, so that like I no longer risk this adding this lack of closure in the convolutions, but because I have already explored this method before and I know it's going to give me the shape of the marginal distributions that I like, maybe this would do away with the problem. Let's see what goes. So the series of steps here is going to be like, okay, first, like let's simulate multivariate normal data. Starting from this slide all the way down, I'm going to be using the MVR norm function of the mass package. If you sort of like pick inside the MVR norm function, you're going to see in one of the lines of code, there's going to be that eigen decomposition and matrix multiplication, which is sort of like say like, this is what's happening under the hood or underneath. So, okay, we start with standard normal variables. I'm going to apply the cumulative density function to each one of those columns of standard normal random variables, so that they now leave, or they become uniform random variables. They now live in 0 and 1. Then I apply the inverse CDF, or the quantile function, of course, using the quantile functions of distributions that I like, the quantile function of the exponential, the quantile function of the chi-square, the quantile function of the gamma, and whatnot. And then in theory, we should end up now with a multivariate distribution that has the correlation or covariance structure that I want, but also has the non-normal distributions as its one-dimensional distributions, one-dimensional marginals that I like. Let's see, you know, that seems reasonable. Let's see how it works out, it plays out in R. So what are we doing here? So we're defining these correlation matrix called R. It's a trivariate distribution. I'm using, as I mentioned, the MVR norm function of the mass package, and with vector of means at 0, and my sigma, my covariance matrix, is going to be this R matrix of core, Biv, Biv norm. Yes, so checks. Values close to 0.5, but not exactly 0.5. Now, this p-norm thing, the thing where I was mentioning to everybody, this is where we get our p-values from, well, no, if they're normally distributed z-test, this could be the pt, pf, or whatever. With a mean of 0 and a standard deviation of 1, if I do these, what I'm going to have as MVU is going to be a whole bunch of numbers between 0 and 1. So each one of these columns of data now is uniformly distributed, but is still a multivariate distribution. And now, because these things have now exist in this sort of like universal translator, which is the uniform, I can now apply my inverse CDF, my quantile function. When I'm keeping this one uniform just for kicks and giggles, so you'll see that I'm not applying any function here. I'm turning this marginal, so it would be this column here back to normal. I'm keeping this, this second column here uniform, which is right here, and I'm turning the third one into an exponential distribution because we rate a lambda parameter of 1. Because why not? I mean, we get to play with what we want, and this is where you would induce your non-normalities and your skewnesses. And long and behold, yep, it gives us the non-normalities that we want. It's like, aha, okay. So now there's no, this is, adding things, central limit theorem coming in and messing up our party here. We're non-normal party. We're keeping things the way we want them. The problem, though, now comes down to the correlation. So the first one remains okay, uniform with normal for something close to 0.5. The non-normal with the exponential, well, that one got a little bit reduced, right? This is now, it used to be something close to 0.5, now something close to 0.45. And the one that's a bit more worrying is the correlation between the uniform and the exponential. So it would be columns 2 and 3, which has now moved from 0.5 to something close to 0.4, 0.43. So as a quick example, actually, if we were to look at how the correlation changes when you apply the probability integral transform, you're going to see, no, this is ugly. Ugly. What I want you to notice here, I'm going to see here, is that the straight line is basically what we would equivalent, or what we would aspire things to be, like that the transformation between the bivariate normal correlation, which is on my horizontal, my x-axis, and the non-normal correlation, which is on the y-axis. Like we would want these blue points to lie as close to the line as they can. But they don't, right? They lie very, very close to the line when, and this is, of course, for the correlation between the uniform and the now uniform and exponential distributions. When the population correlation is low, and especially when it's 0, they're always going to match. But as the bivariate normal correlation increases, the transform correlation, the correlation between the non-normal random variables is biased downwards to the point that whereas you could have a correlation of 1 between normally distributed random variables, you actually have a maximum correlation of maybe about 0.85 between this uniform and this exponential. So the problem here then becomes that once you move away from the normal case into the non-normal world, you no longer have access to the full range, the full theoretical range of the correlation coefficient. So that's going to be a problem as well now. Which is sort of like what I was showing here. And they say like, well, we're in a pickle here. We first try to simulate non-normal variables and then inducing the correlation. That didn't work because the non-normalities changed, right? Central limit theorem started kicking in, the lack of closure and the convolution started kicking in, and now we're ending up with distributions which may or may not be normal, whose properties are not known. They no longer correspond to whatever we thought they would correspond sort of like through our simulation design. Then we thought like, okay, if that's not going to work, what if we start with something that's already correlated, like a very normal case, using the property of closure on the convolutions, use our universal translator, right? Like sort of like random variable 1 becomes uniform through the CDF, and it becomes random variable 2 through the inverse of the CDF or the quantile function. So this is our uniform 0, 1. So we can, like the idea of using our universal translator. So that keeps the non-normality intact, but now the correlation structure changes. So of course, what we want now is a method that will allow us to keep the correlation structure and the non-normality intact. And this is where we cue in the NORTA method. So NORTA method, the NORTA method stands for, of course, normal to anything, which resembles the correlate first, transform later strategy, of course. So this strategy here that we were doing first, but with a slight change, which is like we're in the multivariate normal stage, we're going to use a different correlation matrix from the one that we actually wanted to be in the population. So there's this added step before we only have the three these steps of like bivariate, multivariate normal transform. And now we're going to have multivariate normal with a different correlation matrix. We're going to start calling, this is sort of like the proper term in simulation land, the intermediate correlation matrix. Use that in the multivariate normal step. Apply the probability integral transformation to each one of those column vectors of those one-dimensional marginal distributions. And as you alter the correlations, what's happening is that the correlation matrix, the intermediate correlation matrix, gets altered to give me, the researcher, the user, the correlation matrix that I originally intended all along. This trick of the intermediate correlation matrix is what makes the NORTA method. The NORTA method, it was originally created by this gentleman, Carrier and Nelson. They're not the original developers. I mean, this idea of the NORTA method has been around. I mean, the oldest paper I've seen that at least references something to this comes from World War II. I don't know why, unfortunately, World War II seemed to be a great time for statistics, like linear programming, sequential stopping. All of that came out from World War II, and the seeds of this method included as well. Now, this can be a little bit tricky. First of all, it's because you need to evaluate to obtain the intermediate correlation matrix. It becomes an integral problem. You have to do two integrals, of course, one for each distribution. Now, the integrals, well, that depends on which non-normal distributions you want to use. If you're using well-known distributions, exponential, chi-square, gamma, not a problem. If you use something that's a little bit more boutique or more exotic, then evaluating double integrals might sort of like test you a little bit. It needs to be assembled piece by piece. This is similar to when we're working with polychoric or tetrachoric correlations, right? The matrix itself is not estimated at once because you would need to solve for too many integrals at the same time. So what we do is we break the problem apart by estimating these correlations pairwise, element by element. But of course, when you do this element by element, the risk for non-positive definiteness increases, and it increases very dramatically as the dimensions increase. If you only have like maybe 2 or 3, for those of you, like just as a quick refresher, the property of positive definiteness is sort of like similar to the property of positive numbers. Like, how variances have to be positive in the univariate world. In the multivariate world, we want covariance matrices to be positive definite, meaning, I guess the condition most people test is that the eigenvalues have to be greater than 0. If they are less than 0, then they're no longer positive definite, and that covariance or correlation matrix is not a true covariance or correlation matrix. And this could be a problem when you're doing things piece by piece, because when you're doing everything at once, right, with that matrix, the X transpose X or something transpose something, there's no risk of inducing this lack of positive definiteness. It becomes a problem when you have to put things or evaluate these things piece by piece. And last but not least, it may just not exist. And we're going to be looking at the cases of what to do when these things does not exist. Now, the sort of like running example that I have for this is the case of the log normal distribution. They have very nice properties that allow me at least to show you like worked out examples by hand. Most of the time we have to do these things with computers because the computations get complicated. But let's say we start with now an x, which is like, once again, standard normal. And I'm going to define this new random variable a, where a is, the number e elevated to the power of x. Then we just say that a follows a standard log normal distribution. Now, I'm going to say that I want to create something like a bivariate log normal distribution, whatever that's supposed to mean. Through some algebraic rearrangements, it is not super complicated to show that the correlation between two log normal random variables a and b is obtained by this expression, when rho xy would be, of course, what the correlation coefficient would be had the variables being bivariate normal, right? Because this is how we construct log normal distributions. We start with something that's normally distributed. You do this transformation of e to the power of the standard normal variable, which means that we have a way of connecting the final correlation between the log normal distributions and the initial correlation, or what we're calling now the intermediate correlation, coefficient intermediate correlation matrix of the bivariate normal step on this sort of like what's building up to becoming the NORTA method. If you solve for rho xy, then you would see that, okay, if I want any correlation of my log normals a and b, I just need to sort of evaluate this expression, and this would give me what I want to be, or what should be, the initial bivariate normal correlation. Now, how do we do this in R? Sort of like showcase this example. So once again, I want my final correlation to be 0.5 because that's sort of like what I'm used to. I evaluate this 0.5 for my intermediate correlation rho, and I know then that in my first step of this sort of like build up to the NORTA approach, or the specific instance of the NORTA approach, the correlation matrix, or the correlation coefficient for the bivariate normal should be somewhere around 0.62. Because of course, once I do the exponential, once I transform each one of those columns, that thing is going to get reduced, as we saw on the graph, right, with the lines at the points, but it's going to get reduced back to 0.5, which is what I originally wanted. So simulate bivariate normal data, where of course, what goes into the correlation matrix, or the correlation coefficient, is the intermediate correlation, not the final correlation that I want, as we were sort of like doing erroneously above. I transform each one of the marginals, and when I correlate them, something close to 0.5. And how would this look like? Well, it would look something like this, right? Each marginal is log normally distributed, so it's very skewed. Most of the density of the distribution is concentrated here on the lower left quadrant, and then I have sort of like these clouds of points that are moving along the tails of the log normal distribution. But now this thing is keeping the population correlation structure that I want, that 0.5 that I was working with, and it is also keeping the non-normality of my choice. So yay, at least we finally get something to work that's not the bivariate normal, the multivariate normal case. we're making progress here now. Now, could we simulate from any kind of correlation or covariance structure once we move into the non-normal world? Well, let's say that I want to work with a negative correlation between my log normal random variables. If I substitute this minus 0.5 here and I evaluate all of the expression, you see what I end up with? That is not a number between 0 and 1, right? Because once again, it is not like super complicated to show that when you have standard log normal random variables, the maximum negative correlation that they can have is -1 divided by e. Now, this probably makes more sense if you were to look at, so what did we say? We said that it was, going to be what, e to the correlation -1 divided by, see, let me just check, make sure that I don't sort of like mess up the identity, e to the minus 1 divided by e minus 1. Okay. So e to the correlation of minus 1 divided by e minus 1. So this is what we were saying is going to be the correlation between A and B, correct? Okay, so if I say, well, what if rho is minus 1, it's going to be e to the minus 1 minus 1, e to the minus 1. This is going to be 1 divided by e minus, well, let's call this e divided by e to make sure we're all in the same terms. This is going to be 1 minus e divided by e. This is divided by e minus 1. So I have to do these. These things go together so that I end up with e1 minus e times e minus 1. I can factor out a negative 1 right here, minus 1 for e minus 1 divided e minus 1. These two things cancel out, 1 minus e. This is where the lower bound comes from. And this, of course, applies, and what's interesting, oh, sorry, like I should have stayed here. What's interesting about the log normal case is that as you increase this variance right here, the correlation range shrinks. So it could be a point, you could get to a point, depending on the on how big one of the initial variances is, that you could not even correlate them together. Now, the limits which specify which correlations are or are not allowed within these new frameworks are known as the Fréchet-Höfting bounds. Now, the Fréchet-Höfting bounds, it's just the gift that keeps on giving. Because for some reason, this comes out from the actuarial literature. Like, a lot of people who do math finance are familiar with them. But at least in my research, or like the years I spent looking into this, very few people are aware of them. Which means there's quite a bit of simulation stuff, simulation articles published out there that are simulating data from distributions that are mathematically non-feasible. Because this is sort of like, people were like, the first time I sort of like started teaching that, I said, well, why don't we get warnings from the software? Because nobody's going to give you a warning. It's like, we didn't give you a warning because there's nothing wrong with it. It's within the framework of how mathematics is supposed to work, or the mathematics of these type of distributions in particular. So the next sort of like flash or ping that I tell people to check is that if you're reading or looking into an article that uses non-normality as a simulation condition, and is of course multivariate and using a covariance or a correlation matrix, spend some time checking whether the correlations that they're using are actually feasible. Because you're going to find out that a lot of times they're not. And what usually ends up happening, especially when you do like a software implementation, is that if you select a value that is outside of the allowable range, the Fréchet-Höfting bounds, what the computer is going to do underneath is it's going to settle up on the Fréchet-Höfting bounds. So for instance, a correlation here of 0.5 or 0.6 or sorry, minus 0.5, minus 0.6, minus 0.9 is always going to be mapped to a correlation of minus 1 divided by e. So second thing to check in mind right here. So the question then becomes, well, how do we check for the Fréchet-Höfting bounds? And now for the continuous case, it's a little bit different for the discrete case. It's actually relatively straightforward. You simulate to large samples. I always use 1 million. There's no limit for that. As large as you think large is supposed to be from the distributions that you want to use. And then you're going to sort them in two ways. The first one, you're going to sort this sample from smallest to largest, both for X and Y for both columns of data. And then you're going to keep one of those columns of data sorted from smallest to largest, and then you're going to flip the sorting of the other one for it to be from largest to smallest. You calculate the correlation coefficient in both cases, and for case number 1, that's going to give you the upper bound, the maximum correlation, and for case number 2, that's going to give you the lower bound, or the minimum correlation, of course, including the negative side of correlations, to see whether or not the population effect sizes you're selecting, or the population effect sizes of the articles that you are selecting, are actually correlations that could be in principle, simulated from, or correlation structures that can be simulated from. How does that work for the case for what we're working with here? So step one, the simulation of very large samples. Step two, I'm using the sort function to sort of like sort things from smallest to largest, number close to 1. So I know that at least the positive range is okay, it's allowable, it's allowed to simulate from. And then on the second step, what I'm doing is I'm only sorting B from largest to smallest, so that the smallest values of A are paired with the largest values of B, as opposed to here where smallest values of A were paired with the smallest values of B. And these should be close to -1 divided by E. And yeah, it's close within what, 4 decimal points. So it's a very straightforward method to use, and I don't think it takes too long, or it's not like that crazy for us to be checking these things, whether we are reviewers or consumers of simulation research, to make sure that at least in principle we are working with something that we understand. Cueing now the NORTA method. Well, I showed you a specific case, right? A case where you can actually work these things out by hand. But the NORTA method would not be very useful if we couldn't figure out like the intermediate correlation matrix in the more general sense, so to speak, which is why we sort of like need to rely a little bit more on these sort of like algorithmic approaches to approximate the intermediate correlations. There's a few, like I know of the exponential and the uniform as well. Those intermediate correlation matrices you can figure out like by hand. Most times you won't be able to do that. You have to evaluate integrals at some point. Now, there are 2 packages in R that implement the NORTA method, but only the NORTARA one, which is the one that is not on CRAN, unfortunately, is the only one that solves the tricky problem of the intermediate correlation matrix. I do not recommend people use the NORTA package that exists in R, because that one only changes the marginal distributions. It doesn't give you the right correlation structure. So you're going to be in case 2 of the wrong approaches that we saw earlier. You're going to get the right non-normalities, but the wrong correlation structure. The NORTARA approach fixes that by solving first for the intermediate correlation and then doing the changes and the transformations that are needed. So if we jump back into R, just sort of like a quick demo of how this thing works. The NORTARA package, I'm assuming that people have it installed. First of all, we need to sort of like give it as characters the quantile functions I want to use. In this case, I want the uniform distribution, the F distribution right from ANOVA, the chi-square distribution, and the beta distribution, right? Beta distribution is fun between 0 and 1. It finds its way into a lot of the work that we do, Bayesian methods and whatnot. So that's the first ingredient that it needs. Second ingredient is you need to give it, of course, the parameters of these non-normal distributions. And using this syntax, putting M, I guess M for marginal first. So for the uniform distribution, I'm using sort of like the standard one, minimum value of 0, maximum value of 1. For the F distribution, I'm using equal degrees of freedom for numerator and denominator, 5 and 5. Chi-square distribution, degree of freedom 1 to induce some skewness, and I'm seeing a lot of skewness. Well, the F distribution is skewed on this one. And the beta distribution, which is 2 shape parameters. So I'm using 0.5 and 1. And the third ingredient, of course, is going to be, this is going to be the final correlation matrix, right? The one that I want to use as a researcher. And if I use the function gen NORTARA, it's going to take a little while, and I think I know how idea why it gives me these errors here. I checked, it gives these errors like every so often. I haven't been able to figure out why, because when I check the data itself, it's like, no, it's doing exactly what I wanted to do. So I guess check and ignore. I think I have a sort of like suspicion of why it's giving me an error here, which I will be going into very soon. I check to make sure with the Kolmogorov-Smirnov test that all of my p-values are greater than 0.05, because this is telling me that I am simulating correctly from a uniform, an F distribution, a chi-square distribution, and a beta distribution. And the reason why I think that this was giving me errors is because when I check for the Fréchet-Hefting bound between the uniform and the F distribution, what I get is a number that's close-ish to 0.5. The closer your final correlation is to the Fréchet-Hefting bounds, the more problems NORTA is going to have in giving you or estimating an intermediate correlation matrix, right? Because if the non-normal distribution is already operating at the values that are close to its Fréchet-Hefting bounds, that implies that the latent, well, the first step of normal distribution, its intermediate correlation matrix is going to be close to one of the extremes, either 0.99 or minus 999. And of course, that kind of brings in potential issues of whether or not you can invert the matrices and whatnot. So I suspect that the reason why this is giving me all these warnings is because it's telling, okay, I can handle these, but you're getting really close to asking me to generate data from a correlation structure that I cannot or cannot be feasibly done, which is something that I do like about the NORTA method. Like if you choose something that is outside of the Fréchet-Hefting bounds, it will crash and it will let you know. Say like, hey, you should not be doing this because you're asking me to do something that is not feasible. As if I use this sort of like as an the distribution for what that 1 and 2 for the uniform and the F distribution, say, well, how does this creature look like in multiple dimensions? Well, it looks like this. And this is a fun thing to be playing around with. Of course, you cannot, we cannot show this beyond like 3 dimensions, but you're going to see that all kinds of interesting like blobs and shapes and bimodal distributions end up, because of course, we know how these things look like when you plot the univariate versions of them. When you start plotting the bivariate versions of them, you see all these, I guess, the richness of all the kinds of different shapes that multivariate distributions can have, and why it's such a, I guess, a thorny problem to work with these things, because of course, this is only one type of simulating multivariate non-normal data. There's a whole bunch of other types. I just find this to be the most convenient one for a reason that we're going to be looking at very soon. So this basically sort of like introduces a little bit of what this NORTA method is doing, which is giving me the intermediate correlation matrix and allowing me to sort of like change one of those columns of data into the non-normalities that I want. And when I teach this, because this is sort of like the concentrated version of a 10-week course that I do in Monte Carlo simulations at the University of Washington, say, well, why do we spend like literally like a third of the quarter studying just the NORTA method? And we spend it on it because it's essentially the conceptual basis for pretty much everything that you'll see and you'll ever going to see in the social sciences. One of the interesting aspects, I think, of studying simulation research is that it gives you a very peculiar insight into the culture. And I'm going to be saying because there's a culture of anything, the sociology or the culture of quantitative methods in the social sciences. And you start realizing that we give the correlation/covariance matrix a lot of credit. Like, I mean, think about it. Regression can come from a covariance matrix. SEM, covariance structure models. Literally, like all of classical test theory is something that has to do with variances and covariances. Like the covariance matrix has a very, I personally think after all these years, a slightly unearned privileged position in the world of social sciences, but guess what? These are the rules of the game, and this is what we're going to be consuming as a researcher or producing as a researcher. So I want to make sure you understand these things very well, which means if you understand the NORTA method, you're probably going to understand literally any other method that people can throw your way. Because it all comes down to, I want my one-dimensional marginals to be non-normal, where I get to choose what the non-normality means, and I want my population correlation to be, to still be whatever I want it to be. A noteworthy special case that I do want to spend, and this is sort of like coming in towards the end of the talk, is this thing known as the third-order polynomial method, which was published in Psychometrica by Alan Fleischmann in 1978. Once again, we're sort of like seeing a repeating motif here, is that we start with standard normal variables, and then all hell breaks loose, right? So simulate standard normal variables, And now we define this new random variable y, which is really a polynomial function of my standard normal random variables. So that for coefficients A, B, C, and D, that we'll be sort of like spending some time describing them or figuring out how to find them, we say now that y follows a Fleischmann distribution and with parameters A, B, C, and D, which are the polynomial coefficients needed to transform z, like normally distributed z, to non-normally distributed y. So the question then becomes, well, how do we find A, B, C, and D? And what Alan Fleischmann ended up doing was thinking, okay, I'm just going to work with the skewness that I'm calling gamma 1, and the kurtosis, actually, this should be x's. Kurtosis, right? Because these things are evaluated with respect to the normal distribution, and the kurtosis of the normal distribution is 3. So if we subtract 3 from things, we call these x's kurtosis, because then now we have that the normal distribution has a population skewness of 0 and a population x's kurtosis of 0. Now, the way in which this works was by Fleischmann working out this system of equations right here. There's four equations for 4 moments. The mean, the variance, the Fleischmann distributions are by definition standardized. They all have means of zeros and standard deviations of 1s. The mean, the variance, the skewness, and the excess kurtosis. And it's actually not like, I'm just gonna sort of like work out the first case to see like, oh, so this is what he ended up doing, which is, it was like not super interesting. I need another page. Like not super interesting, but definitely super important. And let's get rid of that. Here. So we said that y is defined to be as this polynomial function, z squared and d z cubed, hence the third order polynomial. And we also assumed that z would be standard normally distributed, mean of 0 standard deviation of 1. If we take the expected value of this whole thing, and applying the linearity of expectation, we can break this apart and say, well, this is a constant, so it comes out. This is the only standard normal, the standard variable, the random variable that we have here. Another constant comes out, z squared plus the another constant that comes out of z cubed. And then we do, okay. So expected value of a constant is still a constant, so that becomes a, plus the expected value of a standard normal random variable is going to be 0, so this goes away. The expected value of z squared will be its variance. This would be 1. 1 times c is c, and the expected value of any odd moment of a symmetric distribution is going to be the expected value of any odd moment of a symmetric distribution centered at 0, like the standard normal case, is going to be 0. So this goes away as well, it's 0. And we see then that the mean or the expected value of this Fleischmann distribution is just the sum of the coefficients a plus c, which of course corresponds to what we have right here. So what Fleischmann was doing is like, okay, now I figured out the equation for the mean. Now let's do the equation for the variance. Expected value of y squared. Of course, all of these would have to be like, all of these things would have to be squared. Solve for it. And then cube and expand. Yeah, no, it's a lot of very tedious algebra, but what you end up with, like, I mean, it pays off at the very end, is a system of equations that where you get to choose the skewness and kurtosis, and then you end up with the A, B, C's, and D's that you can plug in back into the equation and get the non-normality of your choice. The caveat or the thing to look out for in here, because not everybody, I think, has checked this as well, is that excess kurtosis has to be strictly actually greater than or equal to skewness squared minus 2. This is known as the skewness kurtosis parabola, which means that you cannot choose just any values of skewness and excess kurtosis all willy-nilly. There are, if you choose values that, population values that violate these inequality, you're either not going to be able, for instance, the Fleischmann method will crash. This system of equations has no solution. But if you end up with a method that does have a solution, or something like, for instance, there are certain implementations of the Fleischmann method where if you don't get a solution, it just gives you a standard normal random variable. So this, I guess, second or kind of next to last thing to check when you're looking into simulation is that whoever wrote the articles and the papers keeps this inequality or just choosing from values where this inequality is respected. Otherwise, problem. So quick example in R. I'm giving you the system of equations and the little solver, nlib, that is going to find the coefficients that we want. So let's say that I want a skewness of 2 and a kurtosis of 7. I run through all of this. What did I do? Give me 1 second. I end up, of course, when you check for coefs par, these are going to be my Fleischmann coefficients. I'm calling them A, because you're only going to end up with, so it's going to start with B. It's going to give you B, C, and D, because we have this inequality or this relationship, right? That that if the Fleischmann distributions random variables are standardized by definition, which means we're going to have the equation 0 equals A plus C. So you essentially solve for A, which is going to be minus C. And if you apply these polynomial coefficients to my standard normal variable Z, and you ask it for the moments, actually, you're going to see a skewness of something really close to 2 and an excess kurtosis of something really close to 7. How does this look like? It looks a little bit like this, which is kind of what we would expect skewness to look like. Okay, so it's very skewed like here. You have most of the density of the data concentrated on one side, and then it decreases as it sort of like progresses or it moves forward. Another sort of like interesting piece of detail that I have sort of encountered when doing this kind of research is that to be able particularly to match population values of kurtosis, we don't really have very good small sample estimators of skewness and kurtosis. Like even if in the univariate case, you need really large samples, we're talking on the millions before these things start stabilizing. So that always sort of like keeps in the back of my mind is like, well, why is it so variable? Or like, why do I keep on getting like really small values? It's like, yeah, kurtosis is very, very like to see, okay, this one's a little bit bigger. But kurtosis is very variable and requires a very large sample size to be able to like stabilize and then say, okay, so this is actually properly converging to its population kurtosis. Now, so that's for the univariate case. What about the multivariate case? Well, this one was derived by these two gentlemen, Valli and Morelli, 1983, also in Psychometrica, and say, well, let's say that I have two Fleischmann distributed random variables. What they ended up doing, and this is what I'm pretty sure going to be finding in most articles that proposed simulation methods, especially in the social sciences, is that there's going to be the part that sort of like induces the non-normality or tells you how to do the non-normality, and the part that derives the intermediate correlation coefficient, which in this case, of course, it's exclusively a function of the parameters of the Fleischmann distribution, right? The polynomial coefficients of each one of them. But once you have decided on a value of skewness and kurtosis so that you have solutions for the Fleischmann polynomials, all of this becomes a constant, all of this becomes a constant, all of this becomes a constant, and really the only problem that you have to sort of like deal with, which is not really a problem, is solving a cubic equation. This is what would give you the intermediate correlation matrix, which would be, okay, at what level does the bivariate or the multivariate standard normal random variables have to be correlated so that I end up with a final population correlation of my choice. So essentially solving a cubic equation. So previously we found that for a skewness of 2 and a excess kurtosis of 7, these should be the Fleischmann coefficients. This is the Fleischmann polynomial that gives me that non-normal variable y with these moments of our choice. Of course, if you do all of these algebraic operations right here, you're just going to end up with a straightforward cubic equation. And all that we need to do is solve for it. If we jump back to R, which is where we get all of these things. So I'm creating these terms, the linear, the quadratic, and the cubic, and my final correlation that I want, is just 0.5. But I wanted to show you something peculiar about the Vallée-Morelli approach as well, which is once again not something that we see all the time. So I defined this function rho to end up with my final rho, which I wanted to be 0.5, which is essentially just a cubic equation, right? So linear, quadratic term, and cubic term. And when you use the function uniroot.all, I'm telling it, I want you to solve this cubic equation anywhere within the domain of -10 to +10, which you might be thinking, but hey, Oscar, like if you want to end up with a correlation, you have to end up with a number between -1 and 1. Why don't you reduce that number for some reason? I'm going to show you why. You run all of these, and you, of course, will end up with, as per the fundamental theorem of algebra, you're going to end up with 3 solutions, whether they're complex or real valued solutions. Now, of these ones, of course, I have 2 solutions, which are A, negative, and B, greater than 1, which means the third solution, which is a number that is well, I guess within the allowable correlation range, should become now the intermediate correlation, so that we can once again go through this conceptual NORTA method. It's like with the multivariate normal at the intermediate correlation, changing the marginals, and finally end up with a multivariate Fleischmann distribution with skewness, kurtosis, and correlation structure of our choice. The reason of why I wanted to showcase this was because you could be in a situation where there is more than one valid intermediate correlation, right? There is nothing in this cubic equation, this cubic polynomial, that tells it only one of the roots, only one of the solutions is going to be between -1 and 1. You could have 2 solutions between -1 and 1, which would work, or you could have all 3 of them between -1 and 1, which would work. I did a small note on this problem as I was working through because the problem with the Fleischmann approach is that the system of equations also has multiple solutions. So now we find ourselves in a situation, right, where this method that is very popular and that used throughout pretty much most of our simulation studies has this additional ambiguity where there's more than one way to, even using the same method, more than one way to simulate data at the univariate level, and there's more than one way to end up with a valid intermediate correlation. And surprise, surprise, which solution you choose is actually going to influence the type of data that you can generate. But that's a whole other story that we can. I'm super happy to talk about, because that's my program of research, like finding kind of little unsuspecting problems in simulation, so that we can no longer make these mistakes. I guess final graph that I have for this little talk is, well, this bivariate distribution looks quite a bit, right? Like what we were working with the log normal distribution. Most of the data is concentrated in one of the quadrants. Of course, the skewness is not as extreme, so there's a little bit more, it's not all completely plugged into one of the third quadrant. There's a little bit more variance around it, but at the end of the day, it's just the showcasing. Okay, so this distribution is still correlated and has or it distributes the density as we would expect, right? With these points right here in the tail, and most of the density matching where the density is concentrated in the Fleischmann distributions. Fleischmann method, super popular. You're definitely going to see it if you 99 of the time you're going to see it when you grab it or take in an article. But without further ado, and also being mindful of everyone's times, I'm really grateful that you came to hear my talk. I hope you learned at least a thing or two, and I am happy to stay around for like the next 10 minutes or so if anybody has any questions, comments, and the like, or I will pass this now on to Oli and Jenny in case there's anything else that needs to be done. Thank you, everyone.
Thank you so much, Oscar. That was absolutely incredible. Really enjoyed that. Yeah, we've got time for questions if anyone's got any. That's oh, it's almost done a hand clap. I'm going to do a hand clap as well.
Ah, thank you.
Does anyone have any questions at all?
It's a lot of information, I understand.
Yeah.
It usually takes me, like I mentioned, 10 weeks to unpack most of these, but it did feel like I'm like, okay, let's just put them in all together. And
familiarity with it was useful more than anything, I think. So just knowing that this is a problem and knowing that these things that you should look out for, that's if I only picked that up today, which I pick up more, that's definitely a win. I guess, yeah, if there's no other questions, then thank you so much, Oscar, and we'll close it off there. I'll stop recording in case anyone does want to come on the mic and is feeling a bit nervous.